Hello, everyone. My name is Aisha Ali-Gombe from Towson University, and I'll be presenting our paper titled App-Agnostic Post-Execution Semantic Analysis of Android In-Memory Forensics Artifact. This is a collaborative research effort between myself, two of my students, Alexandra and Angela, and Professor Golden Richard of Louisiana State University. Now, I want to begin this presentation with a brief overview of the need for mobile forensics. Mobile devices are increasingly becoming a staple in our lives. They're providing easy-to-use and accessible computing devices across a large swath of humanity. And increasingly, we're over-dependent on relying on the services provided by these mobile devices every day for our personal and professional settings. And thus, this made these mobile devices a crucial source of evidence in many digital investigations. In addition to crime evidence recovery, mobile forensics are also applied or is also applied in the area of post-execution program analysis. In its traditional sense, mobile forensics deals with the recovery of data and forensics artifacts from the persistent storage. However, with the advent of stealthy memory resident malware and the increasing need for other complex programming practices such as encryption, some valuable forensics evidence such as decryption keys, dynamic payload are never written to disk. They are only available in the volatile memory. Thus, in the last decade, there has been a considerable effort in developing innovative techniques and framework for memory forensics. Although frameworks such as volatility have made great impact in the field of study, the effort has largely been targeted to recovering data from the lowest kernel layer. For mobile platform and the Android in particular, now due to the complex layer of abstraction, as you can see in this diagram, between the kernel space and the user space, reconstructing application data structure is becoming almost infeasible. Thus, in recent years, there has been a paradigm shift with focus on developing userland memory forensics capabilities. Now, in the related literature, userland memory forensics techniques can be grouped into three. We have the app-specific, domain-specific, and more generalized technique. In the app-specific category, a unique application is often targeted, let's say Facebook. Its data structures are reverse engineered based on the application-specific logic, which can then be recovered and reconstructed to get the forensics data. Although these techniques are very useful and often adopted by practitioners to provide forensics evidence for common applications, their methodologies are conceived based on the application-specific logic, and thus the resulting recovery algorithm cannot be applied to other applications or even different versions of the same app. Now, for the domain-specific category, on the other hand, signatures for vital data structures, such as images, GUI structures, etc., are recovered. And this is often done by using machine learning, brute forcing instrumentation, or reverse engineering. Now, given a target memory, the memory image is examined or scanned for such structures, which when detected are recovered and reconstructed to get the forensics data. Now, the major drawback of this approach is that they're limited to specialized investigations and or scenarios. For instance, a proposed system for reconstructing GUI cannot be used to reconstruct a network artifact. Now, in a more generalized category, the data structures that host application runtime environments are targeted. The specific of the allocation mechanism for the runtime are then utilized to recover and reconstruct the forensics data. Now, like the domain-specific, these techniques are also app-agnostic, meaning the recovery is not tied to any app. In addition, they're also not limited in their functionality. But the major drawback here is that the recovered data often lacks semantic information that can aid analysts to associate provenance, relationship, and overall contextual meaning to the recovered data. As such, in this paper, we seek to fill in the gap and develop a more generalized and app-agnostic userland memory forensic technique. Here we present Oagent, which comes with algorithm for automated object allocation graph generation and semantic analysis, specifically targeting object flow path exploration and context and scope determination. Now, the goal of our approach is to develop a technique that can be applied to any kind of forensics investigation and can be used for Android program analysis without recourse to any domain or specifics of the application. Now, in the design of Oagent, we built it around the concept of point-to analysis. Point-to analysis is a technique that shows the relationship between pointer references and their allocation sites. In object-oriented programming models such as Java, complex ideas are represented as objects. These objects are created using the new keyword, and when allocated, they are assigned an allocation site. Now let's denote this allocation site as nodes n in a graph, and let's denote the relation between the nodes in the graph as edges. Using points to analysis, for two nodes n1 and n2, a relation will only exist if n1 if n1 is the receiver object of the method that made the allocation of n2, or we can simply put and say n1 holds a reference to n2. Therefore, we refer to n1 as an allocator of n2. Thus, in Oagent, our goal is to track all the allocation sites and establish concrete relationships between every allocated object, which is allocator and allocator of allocator, until all the relations or relationship are finally resolved. Now, starting with the object allocation graph generation, our algorithm our algorithm actually generates a graph, an entire graph for every process image, and we try to establish the relations starting from nodes without any edges. Now, in this algorithm, we recursively search for every reference associated with an object, establishing edges with every new found object. If the new object is decoded as a complex object which holds a reference to another, then its reference is further decoded and added to the node, as a node to the node list, which is further searched to find all of its relations until no further relation is obtainable. Now, the result is a graph that shows the network of object relations with tens of thousands of nodes and edges, as shown in this figure. Well, this object allocation graph can be visualized to illustrate the relationship between the recovered object. However, in order to give meaning to the program, we present 3 semantic analysis algorithms to aid investigators explore more information on specifics of the object of interest. Now, the aim of this algorithm is to efficiently perform path exploration, determine an object's context in the network, and the scope within which an object exists. But before we can find more information about an object, we need to first know where and how the object, or how and where the object exists. Thus, we present a search utility that can aid investigators to find object of interest, such as charts, network syncs, GUI strings, etc. This utility returns the objects, its allocation sites, the metadata, and the object allocation about the object allocation, which can then be used for semantic analysis. Now, starting with the path exploration algorithm, we find the flow path between the source and destination object. Now, but due to the density and complexity of the network in the object allocation graph, there may exist multiple paths between the source S and a destination T, and some of these paths may be interlinked. Thus, we use an efficient k-disjoint disjoint algorithm, which is guaranteed to return flow paths between the source and destination object with no common edges. We further streamline the algorithm to return the shortest of the k paths. As shown in the diagram, the string testing a profile is allocated in the direct path of the Android bundle object. Now, for some complex relation, it is not always the case that an object may have a direct flow path between a source and destination to have an impact. We argue that expanding the search to incorporate all adjacent edges for each node found in the path gives better context to the object of interest. Starting from an object of interest, we recursively search for all the allocators and the predecessors of the allocators and so on. The result is a subgraph. The result here now is a subgraph that gives an expanded contextual view of the object of interest. And finally, there may be need to determine if the object exists within certain program constructs, say a thread, activity, or even a garbage collection route. The object scope algorithm generates a subgraph for each particular program construct and then searches for the existence of object of interest within such construct. Now, with the object allocation graph generation, these 3 algorithms, we implemented Oagent as a standalone forensics tool written in Python with more than 3,000 lines of code. It has 5 modules: the object allocation graph generation, search utility, path exploration, context, and scope determination. The prototype is released on GitHub and has its artifact has been evaluated as functional. The object recovery of our prototype is based on the default region space memory allocation algorithm, which utilizes the base heap utility as released by Droid Scraper. Now, for the evaluation, we tested the effectiveness of the Oagent on 3 salient objectives, which is the performance of the graph, robustness of the search, recursive search, and 2 case studies to illustrate the application of the semantic analysis in digital investigation and program analysis. Now, due to time constraint, I'll limit the evaluation discussion in this presentation to the performance evaluation and only 1 case study. Now, starting with the performance of the object allocation graph generation, we generate a graph with for 14 memory images representing both malware and benign applications. Our graphs were variable in sizes with number of nodes, as you can see in the table, ranging from 35,000 to 300,000, and ages ranges from 45,000 to 500,000. The results here indicate that the processing time, as shown in this graph, increases linearly with the increase in the number of nodes. The average throughput of our graph generation on our test machine, which represents the time it takes for us to do the search, decode, explore, reference, and add nodes to the graph, is approximately about 0.19 megabytes per second. Now, we believe this throughput can be increased substantially with increase in the processing speed. Now, in the case study, we tested the application of Oagent semantic analysis in digital investigations. In this particular case study, which is motivated by real-life scenario where extremists are found to utilize highly secure social networking apps such as WhatsApp, Signal, and Telegram for communication and campaign. We consider a scenario where the Android device is the subject of investigation. A message was found to be deleted on WhatsApp, which uses end-to-end encryption and complete destruction of message feature. The suspect here in this case is not cooperating, and investigators believe the deleted message is crucial and time sensitive. Thus, any available memory acquisition tool, using any available memory acquisition tool such as memfetch, we're able to dump the memory. Then we use our object allocation graph generation algorithm to generate the object allocation graph for the processed memory image, which recovered about 350,000 nodes. We then utilize the string search utility to find strings of interest and their allocation sites in the object allocation graph. As shown in this screenshot, we found a couple of entries for an interesting string that reads Tree of Life, City of Bridges. We then explore the context of the allocation site for one of the instances of this string. Using the context determination algorithm with a depth of 10, we found that this string was allocated within the broader context of the inside SQLite statement. This inside query is also associated with a hash that seems to represent the hash of the message. We then took the hash and further explored its broader context, where we found that another instance of the hash was allocated within the broader context of a delete query. Now, tying all this together, we can prove that the hash represents the message that was deleted, and therefore Oagent was able to recover and provide semantic meaning to this crucial forensics evidence, which otherwise cannot be done using traditional disk forensics. Now, while our evaluation has shown the impact of Oagent in real case studies, one major challenge we face during analysis, it takes a considerable amount of time to weed out noise, and especially in apps with very large graphs. Thus, as part of future work, we are exploring an execution path reconstruction that maps the OAG to in-memory code. This will limit the analysis to only objects allocated within the main program's context. Now, as key takeaway, this paper presents Oagent, a tool for post-execution semantic analysis of Android apps. The presented approach is a generalized app-agnostic technique that establishes relationship and semantic meaning to the recovered in-memory forensics artifact. Using OAG and semantic analysis algorithm for path exploration, context determination, and object scope determination, we've shown that our technique can be utilized for digital investigations and program analysis. Now, that brings me to the end of this presentation. Thank you for listening.